Halfway between Mars and Jupiter, hidden in the cold darkness of the asteroid belt, drifts a world that shouldn't glow at all. It's small, barely 940 kilometers across, and for centuries it was thought to be nothing more than a frozen relic of the solar system's birth. This is Ceres, the largest object in the asteroid belt, and until recently, one of its quietest mysteries. But when NASA's Dawn spacecraft closed in during 2015, the silence was broken by something extraordinary. Blinding white spots beaming from the depths of a massive crater, like beacons in the void. They weren't ice. They weren't rock. What Dawn had found was a planetary light show, one that would shatter old ideas about where life might find a home in the most unlikely corners of space. When NASA's Dawn spacecraft arrived at Ceres in March 2015, scientists were expecting to see a dull, cratered surface more like a lifeless asteroid than an active world. Instead, they were greeted by something astonishing. Bright, glowing patches inside a 92-kilometer-wide depression, now known as the Asteroid crater. Against Ceres' otherwise dark, charcoal-gray terrain, these spots were so luminous, they seemed almost artificial. Initially, the simplest explanation was ice reflecting sunlight. After all, Ceres is cold enough, averaging about 105 degrees, 157 degrees, to preserve frozen water for billions of years. But when the Dawn team analyzed the light spectrum bouncing off these spots, the results didn't match the signature of ice. Instead, the spectral fingerprint revealed something far more surprising: vast deposits of sodium carbonate, a type of salt. On Earth, sodium carbonate is found in places like soda lakes in Kenya or California's Mono Lake, where water rich in dissolved minerals evaporates, leaving behind gleaming white crusts. The very existence of these salts on Ceres implied one startling fact: liquid water must have been involved in their formation, and if there was liquid water, there had to be heat somewhere in Ceres' interior to keep it from freezing solid. This was a game-changer for planetary science. Before this discovery, scientists thought that small, airless worlds like Ceres were geologically dead, frozen relics left over from the dawn of the solar system. But sodium carbonate doesn't form in freezing, inert environments. It forms when water containing dissolved minerals travels to the surface and evaporates, a process that usually requires some form of internal activity. To make the mystery even more intriguing, Dawn's data suggested that these salt deposits were geologically young. Craters on planetary surfaces accumulate damage over time from micrometeorite impacts and space weathering. Fresh deposits tend to be bright, while older ones darken. The Asteroid salts were so reflective that scientists estimated their age to be less than a few million years recent by cosmic standards. In other words, the process that brought these salts to the surface didn't happen in the distant past. It could have been active relatively recently, or even continuing today. But how could Ceres, a body only 940 kilometers across, smaller than Earth's moon, still have enough internal energy to drive such activity? The leading explanation involves a combination of factors: residual heat from Ceres' formation, slow radioactive decay of elements like uranium, thorium, and potassium in its rocky core, and the insulating effect of its icy crust. These factors together could allow pockets of briny water to persist beneath the surface for billions of years. Over time, fractures in the crust, possibly caused by asteroid impacts, could act as pathways for this salty water to rise. Once exposed to the vacuum of space, the liquid would instantly sublimate, leaving behind the shimmering sodium carbonate that Dawn spotted from orbit. In a single discovery, Asteroid crater transformed our picture of Ceres from a cold, inert rock into a world that may still be geologically active, with a watery past that isn't entirely frozen in time. The discovery of fresh salt deposits on Ceres posed an even deeper question, quite literally. If sodium carbonate needs liquid water to form, then where could that water possibly be hiding on a dwarf planet so far from the Sun? At nearly 3 times the distance between Earth and the Sun, Ceres sits in the asteroid belt, where surface temperatures hover around 105 degrees, 157 degrees. Under such extreme cold, any exposed water should be frozen as hard as rock. Yet the bright, reflective patches in Asteroid crater proved that liquid water had reached the surface recently. The Dawn spacecraft's instruments were about to uncover a remarkable explanation. Radar and gravity measurements taken during Dawn's orbital surveys revealed that beneath Ceres' outer crust, made primarily of water ice mixed with rock, there exists a layer that is neither completely solid nor fully liquid. Instead, it is a briny subsurface ocean, or more precisely, a massive reservoir of salt-rich liquid water. This underground sea stretches for hundreds of kilometers and lies several tens of kilometers below the surface. What's more, The water is loaded with salts like sodium, potassium, and magnesium compounds, which lower its freezing point much like road salt melts ice in winter, allowing it to remain liquid even in the frigid environment. The source of heat keeping this ocean from freezing comes from a surprisingly reliable power source: radioactive decay. Deep within Ceres' rocky core, small amounts of radioactive elements such as uranium-238, thorium-232, and potassium-40 are slowly breaking down. This process releases heat, albeit in tiny amounts. On Earth, this heat is negligible compared to our planet's molten core, but for a small world like Ceres, it's enough to keep the interior from freezing entirely. Over billions of years, this constant trickle of heat, combined with the antifreeze effect of salts, has preserved a hidden ocean beneath Ceres' icy shell. Occasionally, something disturbs this underground balance, most likely asteroid impacts or tectonic-like stresses within Ceres' crust. These events can fracture the outer ice layer, opening pathways for the pressurized briny water below to rise toward the surface. As soon as the liquid is exposed to space, it begins to sublimate, turning directly from liquid to vapor, because there is no atmosphere to hold it in place. The water disappears into space, but the dissolved salts remain, crystallizing into brilliant white deposits that reflect sunlight so strongly they can be seen from millions of kilometers away. This process is strikingly similar to the formation of salt flats on Earth, such as the Salar de Uyuni in Bolivia, where water from mineral-rich lakes evaporates under the sun, leaving behind dazzling salt crusts. The main difference, of course, is that on Ceres there is no sunlight-driven evaporation, only the harsh vacuum of space and the alien chemistry of a frozen dwarf planet. By revealing this hidden ocean, Ceres challenges our understanding of where liquid water can exist in the solar system. We once thought oceans required a planet to be warm and Earth-like. Now we know that even a small, distant world can shelter vast, ancient seas beneath its surface, seas that might hold the chemical ingredients for life. Life as we know it requires three fundamental ingredients: liquid water, essential chemical elements, and a source of energy. On Earth, these conditions are met in many environments, from sunlit ocean surfaces to pitch-black hydrothermal vents deep on the seafloor. The revelations from NASA's Dawn mission show that Ceres, a small dwarf planet orbiting between Mars and Jupiter, may also meet two of these crucial requirements: liquid water and chemical activity. This immediately elevates Ceres from a cold, forgotten rock to a potential habitat, one of the most intriguing in the inner solar system. First, there's the matter of liquid water. The discovery of a global subsurface ocean beneath Ceres' icy crust means that, despite surface temperatures cold enough to freeze steel solid, there are pockets where water remains in liquid form. On Earth, water is the universal solvent for life. It dissolves and transports nutrients, facilitates chemical reactions, and provides a stable medium for biological processes. If a similar liquid environment exists on Ceres, even deep underground, it could serve as a cradle for simple microbial life. Then there's chemical activity. The sodium carbonate and other salts found in the bright deposits of Asteroid crater aren't just geological curiosities, they are potential energy sources for microorganisms. On Earth, certain microbes thrive in hypersaline environments, using chemical reactions involving salts and minerals to survive without sunlight. Similar processes could, in theory, occur on Ceres. Additionally, carbon-based molecules have been detected on its surface, possibly originating from the interior. These organic compounds, combined with liquid water and mineral nutrients, create a chemical soup that might be capable of supporting primitive life forms. The third ingredient, energy, is also present, albeit in a subtle form. Ceres does not have volcanic activity or significant tidal heating like Jupiter's moon Europa. Instead, it relies on the slow, steady heat from radioactive decay in its rocky core. While minimal, this heat is enough to keep parts of the ocean liquid and may drive circulation within the subsurface brines. If cracks periodically allow water to rise to the surface, they could also enable chemical mixing, refreshing the ocean with new material and creating potential habitats where life could take hold. Of course, no mission to Ceres has yet detected actual life. The Dawn spacecraft was not equipped to directly search for microorganisms. It could only analyze surface composition and infer geological processes. Still, the combination of water, salts, organics, and heat makes Ceres one of the top candidates for habitability in the inner solar system. Importantly, it expands our understanding of where life could exist. Habitability is no longer limited to large, Earth-like planets in the Goldilocks zone, where temperatures are just right for surface oceans. Instead, Ceres shows that even small, airless bodies can protect vast, dynamic, watery environments deep below the surface and keep them stable for billions of years. For planetary scientists, Ceres is more than just a dwarf planet. It's a living laboratory, a place where geology, chemistry, and the potential for biology intersect. Studying it could teach us not only about our solar system's history, but also about the hidden, resilient places where life might be thriving right now, in the unlikeliest corners of the cosmos. Ceres' glowing salt flats are more than a beautiful cosmic oddity. They're a reminder that life's story might not be limited to Earth-like worlds with sunny skies. In the cold shadows of the asteroid belt, a salty crater is whispering a secret. The universe may be teeming with hidden oceans, and where there's water, there just might be life. That's all for this video, folks. Hope you found this video enjoyable. And if you did, make sure to leave a like and subscribe so you don't miss out on more content like this. We will see you in the next one.